Good morning. Hopefully you have checked out this website here. So the mathlets.org, those Java applets. Yeah, somehow my Firefox doesn't run those ones, so I installed a Chrome and it runs pretty good. Yeah, play around with those applets. So for example, there is one called damped vibration. So basically, this is kind of the simulation regarding one of the homogeneous second-order differential equation, right? Yeah. So even though this one has damped, if you set this b equal to 0, basically that becomes undamped vibration. What's nice out here is it's not only just showing you the response on this window right here. Okay, so this window over here, it has a graph of this this is velocity and that's position there, right? So you can basically drag this, and that'll be your initial velocity and initial position. Okay, yeah. So your response shown here, what not only shows the response of the system, it also shows the response. This is called the phase diagram. Basically, when you plot x and x dot, when you plot the position and the velocity in the same graph, okay, yeah. So that's pretty nice there. So play around with it and then watch the response, right? Yeah. And if you set the b equal to 0, that's basically becomes undamped response. Okay. So you can see this is your initial position. The slope there is the initial velocity. Okay. Yeah. So there are a few more there. There's a forced damped vibration, which I will talk about I think in the next lecture, right? There is also a diagram here calling amplitude, checking the amplitude and phase. And actually, what the animation they're showing at here is using a spring damper system. Okay, yeah. So when you play, I guess. Yeah, you see, this is a sort of like a spring damper system here, but the slight difference is they don't have a mass out here. It's just a spring and a damper. So you can see there's only a K and a B out here. Okay. However, the system here, there's blue color and a yellow color, so it's free to move on both ends. Right? Remember, when we were modeling the spring and the damper, we were talking about the case that both sides are free to move, right? Yeah. When both sides are free to move, they could have independent motion. So there's x1 here, x2 there, so they could have an independent motion. So in that particular case, and if this system here you have a second-order differential equation describes the system, and you give an initial condition, and you look at the motion of this x or y, so that gives you some animation of this, how the both sides of this spring and damper moves, right? Yeah. So it's pretty cool actually. So check this out, right? And I think it can help you understanding the material. Okay. All right, so let's go back to the second order non-homogeneous ODE. In the last lecture, we finished solving the second order non-homogeneous one with constant coefficients using this method of undetermined coefficients. So now let's talk about the other method called variation of parameters. This is not a new name, okay? So we kind of heard of this name when we were looking for the homogeneous system. So here is a general equation that we're looking at. Now, if you remember, when we're using undetermined coefficient method. So this method applies to the case when the coefficients here are constant. Okay? So you have you have constant coefficient. So the question here is, if the coefficient is not constant, and this method will not apply. So the second method here that we're going to look at it, which is so-called variation. Of parameters. So for this particular method, it can be used for both constant and non-constant coefficients. So what do we mean by non-constant? Non-constant is the coefficients that is here. Okay? It's going to be a function of t. Non-constant means we put them in the function y. We function y and then become non-linear. So we're looking at a linear case. So that basically for non-constant coefficients, for example, basically AT and BT are like this kind of case. But where our focus is going to be on the case when they are constant. Okay, so now the question here is now, for variation parameters, what same objective, what would be the general solution for this? Just like undetermined coefficient method. So we know that the general solution. So general solution is y equals to yt. So y equals to yt, and yh is c1 y1 of t plus c2. So the question here is, how do we find the yt, right? Yeah. So it means undetermined coefficient method. How do we determine yt? We use this yt guess, right? Yeah, we guess that, and we modify it if necessary, right? Yeah. So if you, I think I should move down this a little bit here and add one more condition here. When we're using, I think I can move it on, you can, right? So, anyway, not much right. So when we're using undetermined coefficient methods, we like to get that yt. The reason is because this is f of t, right, takes the form sine, cosine e to the power of something, and t to the power of n, right? Or combination of this, right? Yeah. But what if the f? So my question here is, what if the f of t is not going to take this kind of format? What if f of t is a random kind of a function there, very weird function, right? Yeah, it's possible. So if f of t, right? If f of t, right, is some other form, is in some other format. Okay? If f of t is in some other format, then this undetermined coefficient method won't help. Because when you look at your table, you don't have that kind of format, right? Yeah. So then, this is actually one of the reasons we're looking at this second method called variation parameters here. So for example, maybe f of t equal to 1 over tan t, right? So this is has nothing to do with just the sine or cosine, right? Yeah. Maybe it's something else, who knows, right? Yeah. Okay, so if this is the case here, we're going to have to apply this variation parameter. So now you should establish sort of a bigger picture. When you use methods of variation parameters, would you use this method of undetermined coefficients, right? Look like what it looks like is this variation parameters is actually probably applied to more different situations, right? So I mean, if f of t is insoluble, but it doesn't mean that f of t cannot take this one here. If f of t is still sine or cosine or exponential, I can still use this second method here, right? Yeah. So, if I use various parameters, so the question is, what should I give this yt at here? Okay? Yeah. So for various parameters, what you use is this. So you establish or construct yt based on this y1 and y2. So remember, when we're looking for the yh, okay, when you have a double root, right? When you have a double root, what happens is there's only one lambda, right? And you have the e to the power lambda t. That's one of the y1, right? How did we find the y2? What did we do? We multiply this e lambda t with v of t, right? So in this case here, we do a similar stuff right here. So we set up yt as m1 of t, y1 of t. So we vary this y1 and y2, which is the basic solution of the homogeneous one, by applying certain terms through this and try to make this expression to be a particular solution, okay, of this second order ODE. Alright? Yeah, so that's this kind of format here basically is called variation parameters. Yeah. So now the question here is, what would be the M1 and what would be this M2? Right. So we need to find these two. Okay, so how do we find these two here? So we suppose this is our solution, right? So what do we do? Okay, let's take the derivative of the yt. So we're going to substitute the yt prime, and yt double prime back into this second order ODE. Alright? Yeah. So let's take derivatives one here. Yeah, this derivative is a little bit long derivative because you have two types of sincerity. Derivative, you're actually going to have to apply what so if I apply the power rule for the first one here, I've got m1 prime of t y1 t plus m2 prime of t y2 plus m2 of t y2 prime. Alright? Yeah. Okay, so this is a relatively long expression now. Okay. Now imagine if you take the second one, okay, it'll be even longer. Yeah. Oh, that's right. Yeah. Thank you. Okay. Yeah. So one way of going is, I'm not going to do anything. Okay. So what we're doing is we keep calculating this second one here, yt double prime. Right. So that's actually going to work the same way as what I'm going to show you next. Right. So, but the writing is a bit of a long here, right? So now what I'm going to do before I calculate the yt double prime is I'm going to do this. So I look at this one here. I have one term of this one here, one term of this. Okay? Because this is all about the derivative of m1 and m2, and the other two about derivative of y1, y2. So what we're going to do is we're going to let or more powerful, we're going to impose this m1 prime of t, y1 of t, y2 of t to be 0. Okay, so we're going to impose this term to be 0. And you might argue, how could you do that? Yes, you can. You're the user. You can impose anything to be 0. Because the reason is you're looking for m1 and m2. And unfortunately, this is not going to work. Okay? So I'm going to impose this one here to the 0, which means I actually have one equation over here now. Okay? So we're going to make use of this one here. Okay, so let's call this as equation number 1. Right. So if I impose this one now, the yp prime will be much simpler. Right? Yp prime. So the yp prime would just become this term plus this term. Okay. And the next objective is yp double prime. Okay. So again, two-time function, two-time function. Okay. You take the derivative, you need to apply the product rule. So let's see how if I apply product rule m1 times y1 prime plus y1 double prime t m2 prime plus y2 prime m2 y2 double prime. There. Okay. Yeah. Okay, so now we're not going to impose anything at this stage now. Okay, so just let the yp double prime as it is. Okay. So now what we have yp prime, yp double prime. Right. We have the three things in here. So then we're going to substitute the three things that are here back in here. This one. Back in here. So let's call it equation star. Okay. So sub yp prime, yp back, double prime into equation star. All right. So you sub into it. Combine all the similar terms. So let's say if you have a term, every term associated with m1 prime. So you take the m1 prime out, group all the similar terms. Okay. Yeah. So once you do that, we end up with this expression at here. m1 of p. It's very clean and neat actually. y1 double prime plus a y1 prime plus m2 y2 prime y2. Okay, so that's 1 there. And then plus m1 prime y prime plus m2 prime y2 prime equal f of t. Okay? Yeah. So it's actually quite neat expression here. So not that messy actually. Okay. All right. So now let's observe this results that are here, right? Observe the results. So in the first bracket is y1 double prime plus ay1 prime plus by1. What does that give you? First of all, what's y1 and y2? y1 and y2, where they are from? Where are they from? Come again? Homogeneous solution. If it's homogeneous solution, which means the y1 and y2 satisfy which equation? Exactly. So you put a y1 here, this term should be 0, right? Homogeneous means this is 0 here, right? You put a y2 in here, that whole term here should be 0. So if I go back here, so this term should be 0. This term should be 0, right? So you have this term and this term gone. Okay. So all you left is this guy here. Okay. So now I'm going to rewrite it here. That good? Okay. So remember, we already have one equation already. Okay. So now I got the second one here now. I'm going to call equation 2. Okay. So you also need to have a bigger picture because y1 or y2, they are what? They are known, okay? They are known. Because where they're from? They're from the homogeneous one. So you somehow already obtained the y1 and y2. And what we're looking for is m1 and m2, such that this expression satisfies your original non-homogeneous differential equation. And with this operation right here, we end up ourselves, okay, two equations. One equation this, one equation this. Now, if you look at these two equations, what is the coefficient? They're like basically a linear equation here. What's the coefficient here? M1 prime, M2 prime, M1 prime, M2 prime, right? So what's known here? Y1, Y2, Y1 prime, Y2 prime, and of course f of t, right? So you got two equations. How many unknowns? Two unknowns, right? So we should be able to solve for which one? For the M1 prime and M2 prime. Does that make sense? Right? So this is not just a regular linear solution of x and y, but it's more or less like that, right? The pattern there. Okay? So let me rewrite this one alone here. So I have two equations over here. One equation is M1 prime t plus M2 prime t y2 of t equal to 0. Second one is M1 prime t y1 prime t plus M2 prime t y2 prime. There we go, right? So, sorry, f of t. Okay. So two equations, two unknowns. So M1 prime and M2 prime, okay, they're unknowns here. And y1 prime, y2 prime, those are known, right? Those are known here. So you're basically solving a set of a linear equations, right? Except that you're solving, not solving for a number, you're solving for a function. Okay? Yeah. Okay, so how do we solve this one here now? I guess you learned linear algebra. Now, so basically, the left side here, you can write format. So the coefficients here, this is y1, y2. Here's y1 prime, y2 prime. Multiplied by m1 prime, m2 prime. Okay. Right, matrix. So this multiple this multiple this equal to what? 0 f of t here, right? Is that clear? Yeah, a little clear here. From here to here is it clear? Yeah. So if you it's not clear, just multiply this matrix out so you can get that here, right? And of course you should. Yeah. Okay, so solving what I'm solving this one here. So this is basically, let's see, this is matrix A. And this is matrix, let's say, vector V, and this is the vector B. Okay, so we're solving for V. V should equal to V inverse by V, right? So it's a 2 by 2 matrix. And the only thing is, how do we calculate the inverse? Well, okay, so inverse of A inverse, so 2 by 2 matrix. I think you probably learned, what's the inverse of 2 by 2 matrix? Yeah, is what? 1 over AD minus BC, and then here becomes D, yeah. Excellent. Right, here's become negative, right? Yeah. So, if you look at the inverse 2 by 2, I normally recommend you can memorize this one here, but if it's 3 by 3 more than this, use a math lab or calculator. Okay, so in my particular case, here's my A, B, D. So then what I'm going to get here is 1 over determinant A, and allocated here is the D, E is Y2, A is Y1, and minus B minus negative 2. There. So that's A inverse. Right? That's A inverse. So A inverse multiplied by B should give you the solution, which is the vector V at here. Okay? Yeah. Is that clear? Yeah. Yeah, so you will have a formula here, but I think I need to show you this process here, right? So you get better understanding where the formula is going to come from. Now, before I show you the final results here, right? I think one of the questions you should raise is, so you're taking inverse, then you're dividing by the determinant, right? So there's a chance that the determinant of this A is what? 0. So now the only question is, if it's 0, then you won't be able to solve quantum solution here, right? But the question here is, are we going to get the 0 for this determinant in this particular case? You know what I'm saying, right? So what's the determinant here? The determinant is this guy here, right? It's this y1 by this minus y2 by this. Okay? Yeah. Now, I can call you, because this guy here is called also a name here, okay? It's not just regular determinant, it's also called Wronskian. It's also called Wronskian here. Okay. So, in my particular case, okay, I can guarantee that this determinant is not going to be 0. The reason is, what is the relationship between y1 and y2? Exactly. They are linear independent. You remember that, right? When you're trying to find the homogeneous solution, you need two linear independent solutions. Then you can form a general solution, C1y1 plus C2y2, right? So this y1 and y2, and they are Li, okay? They are Li. So because they are Li, and this determinant won't be 0. So if they are linear dependent, okay? If they're linear dependent, if y1 and y2 are LD, which basically means maybe y1 equal to CY2, right? So there's a scale difference. If this is the case, you can verify. You can verify what? Just plug in this y1 and CY2 here, or y2 equals CY1, doesn't matter, right? And you calculate the determinant. It basically becomes 0. Okay? Yeah. So we guarantee that this determinant is not going to be 0 because we're taking y1 and y2 as two linear independent there. Okay. Now, that actually brings additional material right here. You remember when we were talking about one of the lectures, how do I determine whether a set of a function are linear dependent or linear independent? So in that particular lecture, what we did is we multiply each one with the case, right? And add them together and look at whether the only solution for the case are 0. If they are, then they're linear independent. Otherwise, they're linear dependent, right? So now here actually comes the second approach. The second approach is you can form a so-called Wronskian right here, basically the determinant. Okay? And then you check the determinant of that, whether that's going to be 0 or not. If it's 0, then they're linear dependent. If they're non-zero, then it's linear independent. Okay? Yeah. So this is an additional thing there, right? For example, I was asking you, can you check whether y1 and y2 are linear dependent? So what do? We can form a matrix like this and look at the determinant of this matrix. If this determinant matrix 0, then it's linear dependent. Non-zero. So anyhow, let's continue here. And so we found our A here. We found A inverse multiple that. Okay. So then we're going to be able to calculate our M1 prime and M2 prime, right? So I'm going to call this determinant this guy. Right. I call it Wronskian here, right? So I'm going to use a WT, okay, to denote this determinant. Okay. Then my V, which is M1 prime, M2 prime here, okay, that equal to A inverse B. So if you multiply things out, okay, you end up with this quantity here. Okay, so end up with this quantity. So WT is the determinant. Okay, determinant is this. It's y1, y2 prime minus y2, y1 prime. All right. Now, what is my solution? My solution here is, now this is not a solution for M1, M2. This is a solution for M1 prime and M2 prime. Okay? Yeah. But what we're looking for is what? Solution for M1 and M2. So what do? So this guy equal to that guy equal to that. Okay, you need to understand M1 prime T basically is what? dM1 over dt, right? Over dt. So this guy equal 1 over WT over f of t. Alright? So multiply the dt to the other side, and this side becomes dm1, and then you integrate both sides. So we have m1 of t equal integral. It's negative here. I will take negative here. 1, 2 here. Sorry. I made a mistake. This is not a divide here. This is multiply. Okay, multiply here. Okay. So this is multiply. Okay, let's multiply here. Okay. Yeah. So we have f of t here, and over wt dt. Okay. So that's your m1 of t. So similarly, m2 of t. M1 over wt dt. There. So you have this formula now, and you will have this formula. Okay. Yeah. So you will have this formula, but before you use this formula, you have to calculate which one, this WT here, right? Okay, so this WT basically is this quantity, and the WT is the matrix, the Y1, this matrix is here, right? This matrix. So my final exam, normally the formula is, I'll give you this one. I don't remember I gave you this matrix or not. I think I need to be able to know this matrix here, the Wronskian, right? Yeah. So one of the common mistakes is a lot of students here y1, y2, y1 prime, y2, y2 prime, right? They forgot to calculate the derivative here, so they make it a y1, y2 again. So basically, things are not right here. If you make a mistake here, you won't get the right result set here, right? Yeah. So the key point here is get the W right first. Is that clear? Yeah. So that's basically variation of parameters. So all it boils down to apply these two formulas. All right? Yeah. So let me show you an example. Y double prime plus y equal to second t. Okay, so second t is 1 over cos t. So this has nothing to do with the regular sine and cosine or exponential. So then that undetermined coefficient methods won't help in this particular case. We need to use the variation parameters. And before we do that, as always, your first step is to obtain the y1, y2, which come from this homogeneous one, so characteristic equation first. This gives lambda equal, yes, positive minus 3. Okay? And that means YH will be A1 cos t sine t. So what is my Y1 at here? And what is my Y2 at here? Cos t here, sine t. So that's another essential skill here, right? I think you're all comfortable. You're all getting comfortable with writing down the general solution for the homogeneous one, but you should also remember what's behind this one here. There are two solutions, right? There are two linear independent solutions. One is y1, one is y2, right? So that's actually one of the mistakes. Many people are able to write down the yh, but they can't figure out what's y1 and y2. And sometimes I see people write this y1 equal to c1 cos t, c2 sine t. Okay? And that's not right. Alright? Yeah. So y1 and y2 are not a general one, they are just some certain kind of particular one there. Because if you do have a constant here, right? If you do have a constant here, it's not a very significant, not going to make you a very significant error, but you're going to have a constant basically carry out along this calculation there. Okay. So technically speaking, I don't have to take y1 as cosine t. I can take y1 as what? Maybe 3 cosine t, right? Yeah, technically speaking. Okay. So this is y1, y2, and we're going to let yt to m1, y1 plus m2, y2. Okay. So how do we get the y and y2? And before we solve that, we have to form our matrix A, which is forming y1 is here, y2, y1 prime, y2 prime, right? So that's how the A matrix is formed. So calculate derivative based on this y1, y2 at here. First row is cos t, sine t. Second row derivative, so negative sine cos t. Okay. So then we need the determinant of this matrix. So determinant of this matrix is just this multiplied by this, subtract this, multiplied by this. So what do we have? 1. Okay. Alright, so now you got 1 is actually quite simple here, so then we apply the formula here now. So apply the formula because we got all the information. So m1 is integral y2 over so wt is 1 and y2 is sine. So take out the sine in here. F of t is 1 over cosine dt. Okay. So for this integral here, what's this integral? Or what would you use to calculate this integral? Oh, damn, I forgot to plug this in here. Yeah, so the sound won't be nice. So how do you calculate this integral here? Yeah, exactly. So I think now you can use my technique. So basically substitution, right? Yeah. So if I change this dt, this is cosine here, and sine t dt basically is a d is a negative this, right? But I can take the negative sign out, and that basically is this. Okay? Yeah. Is that clear? Now, are you comfortable with this symbol here now? D bracket something. Right? D bracket something, basically it's negative sine t dt, right? Okay. So, you got u at u, basically the same thing here. What is that equal to? Ln absolute value cosine t. Now, you don't need to plus a c here, okay? You don't need to do that. The reason is we don't need a general m. We only need 1, right? We need 1, that's enough. You want to plus 1, that's okay, right? If you want to plus 2, that's okay, but just don't plus a 2. Just don't plus a c, right? Yeah. But of course, you want to pick an easy one, so I guess just plus a 0. That would be great, right? Yeah. And m2 is y1 f of t over wt dt. And that's cosine t 1 over cosine t dt. Well, that's even better. So we got t, right? Got t. So then overall your y p is m1, it's this term, multiplied by y1. y1 is cosine t, and plus m2, that's t, multiplied by y2 t, which is sine. So that's your particular solution for this non-homogeneous one. Okay? Yeah. So last step is your general solution is yh plus yp. Right? Okay? Yeah. If the question gives you initial condition, then you calculate y prime, y double prime, sub the initial condition into it. Actually, you don't need to calculate y double prime. So just y and y prime. Then obtain this constant c1 and c2. Yeah, take a look at it. Is that good? Yeah. So I have one more example here. I don't think I'm going to go over now, but basically the other, I'll just let you know what there's a subtle difference to it here. Okay. So here is another equation in here. Y double prime plus y equal to sine 2t. So when you look at this one here, I think what jumps in the mind? What would you use? So you look at this function here, which is sine 2t. I guess you can use what? The undetermined coefficients, right? Because this is the kind of a regular format we have in the table, so we can take a lucky guess, right? So basically, you can use two methods. Both you can use this variation parameter. You can use the undetermined coefficient to solve this one here, right? But take a look at the lecture notes here, okay? So what happens is, when you use the two different methods, you end up with, particularly when you have this trigonometries here, you end up with two different expressions. So what appears to be two different solutions, all right? Two different solutions when you use these two methods. Let me finish this. Yeah. So when you have two different solutions, you shouldn't panic here, right? What happens is when you have a trigonometry, a lot of times there's trig identities. They're actually the same thing. Okay, they're actually the same thing. Okay, so take a look at that examples. Yeah. Yeah, that's right. That's usually the general approach here. But it's really hard to say which method is easier for the calculation code. Sometimes this variation parameters actually turn out to be easier to handle. Yeah. So then, which one is good or is hard to say? Yeah.
So basically, like we're saying, to use those methods or use like those methods that